welcome back. Today, we're cracking open the playbook of the modern data engineer. These are the architects building our digital world, the unsung heroes making things like AI and business analytics actually work. So what does it really take to build that infrastructure? Let's dive in. First things first, let's talk demand. The U.S. Bureau of Labor Statistics projects a jaw-dropping 35% job growth for data engineers by 2032. Now, to put that in perspective, that's nearly 10 times the average growth rate for all jobs. We're talking about 17,700 new openings every single year. It's pretty clear that in an age of big data, the people who can tame it are needed badly. Okay, so the demand is off the charts. But what does a data engineer actually do day to day? It's so much more than just being a plumber for data. It's really about being an architect, designing and building the strong, scalable information systems that are the absolute backbone of any modern company. So here's our game plan for this explainer. We're going to start with the basics, then get into how data is stored and modeled. From there, we'll jump into the engine room with Apache Spark. After that, we'll see how all these pieces fit together to build data pipelines, how to tune them for peak performance, and finally, how to make sure the data is actually trustworthy.
All right, section 1. What is data engineering? Let's use an analogy here. Think of a data engineer as a master chef. They don't just hand you the final plate. No, they source the raw ingredients, they prep them, clean them, and then combine them into something valuable and refined, ready for data scientists and analysts to consume.
You can really boil this whole process down to 3 key pillars. First, you've got data production. This is where raw data is just created everywhere. Think app databases, IoT sensors, clicks on social media. Then comes the important part, data transformation. This is the cooking step where engineers clean, organize, and structure all that messy raw data. And finally, you have data serving, where they make this polished, useful data available for things like dashboards or machine learning models. You know, a really core concept you have to understand here is the difference between 2 kinds of systems, OLTP and OLAP. OLTP systems, that stands for online transaction processing, are what run the business day to day. When you place an order on Amazon, that's a transaction. These systems are built for speed, for writing data really, really fast. On the other hand, you have OLAP, online analytical processing. These systems are for analyzing the business. They're designed to scan and crunch huge amounts of data for reports. A huge part of a data engineer's job is building the bridge to get data from those OLTP systems over to the OLAP systems. Section 2, storing and modeling data. Okay, so before you can process anything, you've got to have a place to put it and, a plan for how to organize it. This is where the architectural blueprints come in. This slide shows a really important evolution in data storage. On one side, you've got the data warehouse. Think of it like a perfectly organized library. Everything is structured, cataloged, and ready for business reports. But on the other side, you have the data lake. This is more like a vast lake. You can pour any kind of data into it, structured, unstructured, logs, images, you name it, all in its raw native format. And that flexibility is a total game changer for modern data science.
So inside that data warehouse, how is the data actually modeled? 2 classic designs are the star and snowflake schemas. The star schema, on the left, is simple. You have a central fact table, maybe with sales data, and it's directly connected to dimension tables, like products or customers. It looks like a star, right? And fewer connections means faster queries. The snowflake schema on the right goes a step further and breaks those dimension tables down even more. This saves storage space by reducing repeated data, but it also makes queries more complex. It's a classic trade-off. Do you want speed and simplicity or storage efficiency?
Okay, section 3. Now we're getting to the engine room. If data engineering has a superstar technology right now, it is, without a doubt, Apache Spark. It's pretty much the dominant force for large-scale data processing today, and for a very, very good reason. To really get why Spark is such a big deal, you have to look at what came before it, Hadoop MapReduce. Now, MapReduce was revolutionary, but it was also kind of slow. And that's because after every single step, it had to write all the data back to a hard disk. Spark's game-changing idea was to do all of its processing in memory. That one shift makes it up to 100 times faster, which totally changed what was possible, especially for complex stuff like machine learning. Now, inside Spark, there are a couple of ways to represent data. The original way was with an RDD, or Resilient Distributed Dataset. Think of it as a raw, flexible list of items. But the modern way, the standard now, is the data frame. It organizes data into columns with names, just like a spreadsheet. And that structure is everything. Because Spark knows what your data looks like, it can automatically optimize your code behind the scenes to run as efficiently as possible. So how does Spark work all this magic? Well, it starts with transformations. A transformation is like writing down a single step in a recipe. When you tell Spark to, say, filter some data or map a function to it, you're not actually doing any work yet. You're just building a plan, a list of instructions for what you want to do later on. The second piece of this puzzle is the action. An action, like telling Spark to count the rows or collect the results, is the command that says, okay, recipe's done, execute the plan now. It is only when you call an action that Spark finally kicks into gear and actually runs through all those transformation steps you defined. And this brings us to this incredibly powerful idea called lazy evaluation. By waiting until you call an action, Spark gets to see the entire plan, the whole recipe all at once. It builds a map of all the steps called a directed acyclic graph, and this lets it make super smart optimizations, like combining steps or reordering them to create the fastest possible execution plan. This right here is the secret sauce behind Spark's amazing performance. Section 4. Building the data pipeline. All right, let's put all these ideas together. It's time to see how data engineers use tools like Spark to build what is essentially an assembly line for data. The classic blueprint for this assembly line is ETL, extract, transform, and load. It's pretty straightforward. First, you extract data from all your different sources, databases, APIs, whatever. Then, you use a powerful engine like Spark to transform it. This is where you clean it, join it, and shape it into a useful format. And finally, you load that clean data into a target system, like a data warehouse, where it's ready for analysis. Of course, engineers aren't building these pipelines from scratch. They have a whole ecosystem of amazing tools. They might use something like Apache Kafka for bringing in real-time data streams, then use Apache Airflow to schedule and manage the entire workflow, and finally load that data into a cloud data warehouse like Snowflake or BigQuery, often using storage like AWS S3 to hold it all. Section 5. Optimizing for performance. So, a working pipeline is one thing, but a fast and efficient pipeline, that's the goal. This is where a data engineer's deep technical skills really shine. In the world of distributed computing, systems like Spark have one primary enemy. There is one major bottleneck that slows everything down, and it's an operation called the shuffle. This is the biggest performance headache a data engineer has to deal with. So what in the world is this shuffle? Well, as you can see here, some operations are easy. We call them narrow transformations, like map or filter. They're fast because each computer in the cluster can work on its own little chunk of data independently. But wide transformations, like a join or a group by, that's a different story. To group all the records for a single key together, Spark has to physically move data between computers over the network. That data exchange, that is the shuffle, and it is very, very expensive. Minimizing shuffles is the name of the game for performance tuning. To control all this, engineers have a bunch of configuration settings. Think of them as tuning knobs for the Spark engine. They can adjust how much memory each worker machine gets, how many CPU cores it can use, and even fine-tune how data gets partitioned during a shuffle. Getting these settings just right is part art, part science, and it's what separates a good data engineer from a great one. Section 6, Data Governance and Quality. And finally, look, none of this high-speed, fancy processing matters one bit if you can't actually trust the data. This last piece of the puzzle is the foundation that makes sure all the hard work is built on solid ground. And it really comes down to these 3 pillars of trust. First, data lineage, which lets you trace data all the way from its source to its destination. It's absolutely critical for debugging when things go wrong. Second is data security, things like encryption and access controls, to make sure only the right people see the right data. And finally, data quality, constantly running checks to make sure the data is accurate and reliable. After all, decisions made on bad data are always bad decisions, period. And that brings us to the future. We've just gone through the playbook for today's data engineer, but with the absolute explosion of AI and large language models, which are incredibly hungry for data, how is this role going to have to adapt? What new kinds of data pipelines and what much higher standards of quality will we need to build the foundation for the next generation of artificial intelligence? That's easily one of the most exciting questions in tech today. Thanks for joining me.